如果有一些有的不太相信嘛，你说你名字是吗？没有啊。香港就是这样。OK， 中文名字，英文名字叫马口。
好，上好了，这上了对不对？好。
OK。
好，那非常欢迎当然各位老师跟同学来参加礼拜一的 program。好，那非常欢迎我们那个 professor 上，然后他要演讲我们这个主题是 Homological Symmetry by Gross-Siebert program。好，我们欢迎他。
Thank you for the invitation. Because I'm more familiar or more comfortable with English, so I'm sorry that. Please forgive me. I'm going to speak in English. And my topic today is homological mirror symmetry via the Gross-Siebert program. To begin with, okay. So what is mirror symmetry? Mirror symmetry is a connection between symplectic geometry and complex algebraic geometry. So in this talk, maybe you are an algebraic geometer, maybe you are a symplectic geometer, but mirror symmetry is a bridge that interchange these two theories. And it's a physics theory discovered by string theories. Okay. And mathematically, it was proposed by Conservage, the so-called homological mirror symmetry. Is defined. What means by mirror is that the derived Foucault category of a symplectic manifold is quasi-equivalent to the derived category of Brillouin sheets. What does it mean? Let me just briefly recall, or if it is new to you, the Foucault category is a category whose objects are Lagrangians of manifold. Next. So if you don't know what is Lagrangian, it's just if the dimension is 2n, then the dimension is n. And then you have a 2 form. You restrict this 2 form to L, it is 0. That's the Lagrangian condition. And the mirror side, we have the derived category. So it's a well-known algebraic object. Object here is a coherent sheaf. If you are not familiar with sheaf, then object here, they are vector bundle, if you like. Holomorphic vector bundle. Okay, so in the beginning, you just feel like they are totally different things. But that's the magic of mirror symmetry. Would you mind? Because it's a little bit. So, but geometrically, what does it mean? So it was explained by 3 people, Schrödinger, Yao, and Saslow. They proposed that mirror symmetry is T-duality, meaning that you can obtain this correspondence, or you can even construct from X to X check by taking due torus vibration. And here's the photo or picture, drawing, whatever, that how to teaching you how to go from one side to the other side. You start with an integral alpha manifold, meaning that is a manifold, transition functions are alpha maps. And integral means your matrix is invertible over integers. So you take the corresponding cotangent bundle, and then because it's integral, so you have a corresponding local system. You have a lattice inside. You divide it out, you get a torus vibration. So this guy has a natural standard symplectic structure, and so this is a symplectic manifold. And the fiber, under the fiber, you have a natural vibration. The fiber is a torus. And this is an elementary fact that if you take the so-called dual torus, you take this, the pi 1, and then a tensor with u1, the Hom between them, then a point here will give you a flat line bundle on the dual torus. And this guy is the tangent bundle of B, which is due to this guy. You have the dual lattice and quotient it. And because the transition function is affine, you can check that this guy has a natural compressed structure. And how does it explain the homological mirror symmetry? If you have a point, you get a flat line bundle. So if you let this point move horizontally, then you have like a lot of line bundles, right? Each point you have a line bundle. So you let it move horizontally, you get a family of line bundles. So, but what is moving horizontally? Moving horizontally means you have a section. And here, turns out all this family of line bundles, they actually glue to a line bundle on the total space. And more importantly, you can write down the equation, and you can just calculate that the Lagrangian section is the section is a Lagrangian, meaning that you satisfy this condition, if and only if the mirror bundle is holomorphic. So it beautifully explains how the two sides transform from one to another. So that's the fundamental picture provided by SYZ. And now we should switch ourselves to algebraic geometry. So based on the idea of SYZ and all the other people, Mark Gross and Gross-Siebert, they launched a program to understand mirror symmetry by using tropical geometry and toric degeneration. And roughly speaking, as the name suggests, a toric degeneration is a flat family of algebraic rarities whose central fiber is a union of toric rarities. So toric rarity is something very combinatorial. And then, as toric rarity, it always comes with a fan. So you can glue all the fans together according to how they intersect along the toric divisor. And then, the resulting object is an affine manifold, but you possibly have singularity. And the fan structure will give you a polyhedral decomposition. So I will show you a photo later. And if the whole family is polarized by an ample line bundle, then the central fiber is also an ample line bundle. And we know that on each toric strata, on each toric rarity, ample line bundle are classified by a strictly convex piecewise linear function. So now you have a lot of toric rarity, so you have a lot of functions. And each of them are strictly convex. And if you know if you have a strictly convex function, you can define the discrete Lagrangian transform. And this will give you another set of such data. And pictorially, the Gross-Siebert program constructs mirror pairs by the following picture. So you start with a smooth object, whatever color BL you love. So you start with an X, and then do a toric degeneration. So this guy is a union. This X0 is a union of toric rarities. And then to turn this, you look at, for example, no matter you look at the polytope or the fan. So if you look at the neighborhood around this point, you have 3 rays. And this rays is like, you give you a fan. You give you a fan structure. Each of this point give you a fan. And this line, if you look at the line of this fan, that means you just collapse the whole thing and let the 2 other faces become 2 rays. Then it's a fan of P1. So for example, this guy is actually union of 4 P2 along all the P1s. Okay, so this is the discrete data that we obtained from tropicalization. Okay, this process is called tropicalization. And then I take the so-called discrete Lagrangian transform by using this function, and this function will turn the big cell like this dimension 2 face into a point, and the point into a top dimensional face. Okay, so big things become small, small things become big, and then you repeat the procedure. So you try to construct this guy by taking, just redo this, which means you just take all the toric variety and then glue them together according to the strata. And this is the final part, which is the hardest part, that what Gross and Siebert did, is how to go from this singular space, because it's a union of toric variety. So this guy is very singular. And you do a smoothing. Okay, this is the most non-trivial part of the whole Gross-Siebert program. And then these two will be mirrored to each other. Okay, remember, not these two. These two will be mirrored to each other. Oops. Okay. Okay. So we mentioned a lot of things: homological mirror symmetry, SYC, and Gross-Siebert. So the first thing, we know that SYC explain mirror symmetry, but how about Gross-Siebert? How do we explain homological mirror symmetry by the Gross-Siebert program? And we have seen in the SYC picture, Lagrangian section will be mirrored to holomorphic bundles, line bundles. So our expectation is if you have several layers, so section is like this, right? Section is like this. This is a section of a vibration. So if you have a multi-section, that means you have several layers. Then, well, one line corresponds to a line bundle, two lines then is a rank 2 bundle, right? So we should expect multi-sections, which means the following diagram. You have a Lagrangian immersion, so that this composition is a branch covering map. Okay. Should map Lagrangian multisection to a holomorphic vector bundle. That's the expectation by SYC. But it's much more complicated because of the branch locus. This branch locus will contribute a lot of non-trivial so-called instanton corrections in the SYC transform. And this is very hard, especially if your vibration, the SYC vibration, if this one has singular fiber, you don't even know how to define it. Okay, so far there's no proper way of defining the so-called family floor if you have singular fiber. So to get rid of the difficulties of the instanton, we first tropicalize our multisection. So what does it mean? First of all, of course, we need to ask ourselves what can be tropicalized. And the simplest object on a toric vector on a toric variety, they are toric vector bundles, which means equivariant bundle. Okay. So they are torus equivariant bundle, and for instance, all line bundles are toric. So if I start with such a bundle, what do I mean by tropicalization? So we can use the equivariant structure on each affine chart. And then same thing, he construct a cone complex. As the name suggests, it's a collection of cones inside a topological space with a map, mapping cones to cones isomorphically, and a multiplicity map, so that if you take the trace of this map, which means you sum over all the possible pre-image, then it's R. The R is exactly the rank. And finally, and the most important object, is a piecewise linear function on the domain. Of course, piecewise linear means according to the cone structure. Let me just give you an example. It's too abstract. So let's consider the following exact sequence. Well, the map is just mapping to the homogeneous coordinate raised to the power A. Okay. So you have this map, so ABC need to be positive. You take the quotient, this is a vector bundle. And you know they are line bundle, so it's toric, so the quotient is toric. And the data that I just mentioned abstractly, geometrically or pictorially, you can picture them like the following. So here, you can see, ignore all this labeling. This is a twofold cover. This is a fan of P2. And this is a twofold cover. Okay, in what way? For example, this sigma 0 is a little bit blurred.
this sigma 0 and this sigma 0, you have two layers, you map to this sigma 0. Sigma 1, 1, sigma 1, 2, up to sigma 1, etc. And this point is the point that just have one, this point is the point that you just have one pre-image. So this map actually is the map Z map to Z square, like you study in complex analysis. And the function here that I put on top is it's determined by the equivariant structure of this guy. The function is labeled in the following way. So I choose coordinate because C1 plus C2 here. Sorry, people cannot see over there. So I choose a coordinate because C1 plus C2. And then, so you know, they are just linear function. So I regard this linear function upstairs and glue all this linear function together. As you can check, this function is actually continuous because, for instance, this one changed to this one. This line is what? This line is exactly this line. This line is cos C1 equals to 0. Cos C1 equals to 0, so it doesn't matter, the coefficient change. So it bends. So it bends from here to here. So this is a piecewise linear function upstairs. Okay, so this is the object that we obtained, that Ping obtained. So we give him the name because it looks exactly like a multisection. You have a cover, okay? The picture just shows you that it looks like a cover. So in multisection is the data that I just described, but abstractly. And the data that I just obtained from a bundle, we just give it a name, the associated tropical Lagrangian multisection, or a tropicalization of vector bundle. And you may ask what data that this guy captured. The answer is that they are equivariant Chern classes. In a sense that if you have two toric bundle, this is E2. If you have two toric bundle, then the associated multisection are the same if only the equivariant Chern class are the same. Okay, so it's a very combinatorial or discrete data that you cook up from a vector bundle. So after I define for multisection over a fan, I can immediately generalize to the data that Gross-Siebert obtained, this BP. But to do this, we need to know the language of tropical space, which is a very schematic definition. So you have a Hausdorff paracompact topological space, and you have two sheaves. One of the sheaves is locally is just piecewise linear function of some polyhedral space in Euclidean space. And this affine function is a choice of subsheaf, so that it contains the integer. So you think of this one as affine function, and this one as piecewise linear function. So in particular, affine function are piecewise linear, it's just smooth, and then you take the quotient. Okay, this is the thing that we are interested. So you get this quotient sheaf, okay, which is a multi-value piecewise linear function. And the basic example is, of course, the Gross-Siebert construction. This BP, they are automatically they have a natural tropical space structure. So tropical Lagrangian multisections is nothing but a morphism between them. Well, you may require to be surjective. And then you have a collection. Previously, we have a collection of cones. Now we have a collection of cells. And this cell will be mapped isomorphically to this collection of cells. And the mu specify the multiplicity as before. And you have a section here. Okay, so this is a piecewise linear multi-value piecewise linear function. Well, the reason that I define like this, why it need to be multi-value, is because, for instance, if R is compact, it's easy to show that you seldomly support piecewise linear function. So you need to be multi-value. And secondly, this multi-value function has a geometric meaning. You think of this as the Lagrangian potential function. And you know the potential function of Lagrangian is not single value unless it's simply connected. So we need it to be multi-value. It to represent the Lagrangian itself is actually non-trivial. Okay, so this is the basic idea of this tropical multisection. And as the name suggests, we should expect, well, SYC tells us that multisection transform to a vector bundle. So if we tropicalize it, we should also be able to build a locally free sheaf now on the central fiber. The first observation is cannot be possible, because as I said, this data is very discrete. So it's just some combinatorial data, but you know sheaf has a big moduli. And moduli space is like continuous or topological things that is not discrete. So how can we build such a space? Then we need to introduce the moduli parameter, which is the continuous data. And in the simplest case, in the toric case, Kaneyama, he already defined what this data means. So he started with combinatorial data, but in our language, it's nothing but just a tropical Lagrangian multisection. And then he introduced some continuous data. Due to the time reason, I don't have time to introduce this. But this data allows him to build a toric vector bundle over a toric variety. But we are dealing with union of toric variety, right? Toric degeneration, central fiber are union of toric varieties. So on top of Kaneyama's data, let's say on each toric strata, the Kaneyama's data exists. We still need extra gluing data to glue this locally free shift or this vector bundle together. And these two data, let me just combine them quite like bulk D, and this will give us a sheaf, okay, which is locally free on the central fiber. Again, well, I tell you this thing determine the bundle, but when such data exists, of course this is a problem. First thing is in dimension 2, which is the thing that I'm interested in the following talk. Well, in this talk, once the Kaneyama's data are given on each maximal strata, the gluing data between the lower dimension strata always come for free. The main reason is because all line bundles split on P1. So in 2 dimensions, all we need to do is to find Kaneyama's data. And this will be done after the algebraic part. Okay, so I try to split the talk into the algebraic part and the symplectic part. So we'll address the existence of Kaneyama data in dimension 2 at least. We use purely symplectic geometry argument, and of course mirror symmetry. So let's say we are given all the data. Now we want to smooth this sheaf, right? Because according to the Gross-Siebert program, we need to rebuild our space by smoothing the space. And now if I have a sheaf, I also need the sheaf to smooth together with my space. And let's just focus on the simplest case, rank R and dimension 2. And by further subdivide the polyhedral complex, so you have a polyhedral decomposition, you further subdivide in dimensional 2, you can always assume after taking a subdivision, which corresponds to further degeneration, this guy is elementary. In the sense that if you take the dual, they are all elementary simplex. Okay, so they are triangles without interior vertex. Okay, in dimension 2. So if you further subdivide, actually make the space simpler. It's just a union of P2s, okay, because it's an elementary simplex. And you know that elementary simplex, the only mirror, the only toric variety that associated to it is the smooth projective space or projective plane in dimension 2. And the smoothability theorem we want to use is the following. Due to Kok-Wai-Chen and Jimeng Ma, if I give you a perfect complex over a so-called toroidal space, forget about toroidal space if you like just this space. And if it is smoothable, the space itself is smoothable, which has already been done by Gross-Siebert. Then the only obstruction to smooth the perfect complex is the traceless. This 0 stands for traceless of the second extension group. Okay. And because we are not dealing with perfect complex, we just have one locally free sheaf, then we can apply Serre duality to turn H2. In this case, this is just this guy. Well, this is not the traceless one, but if you put in the diagonal part, then it's just this one. And then we apply Serre duality, and because this guy is a log Calabi-Yau surface, I didn't talk about the log story here, but believe me, that means this guy has a trivial canonical sheaf. Then we apply Serre duality, then you go to H0, okay, because it's a surface. So H2 becomes H0. I missed the deal here, but anyway. Then unobstructedness, which means the vanishing of this guy, is equivalent to the simplicity of the bundle. Okay, so the vanishing of this guy is just by showing that you have no non-trivial endomorphism. They are all scalars. So in dimension 2, well, branch point, right? Branch locus are always points, and they are always assumed to be the vertex of the polyhedral decomposition. And but still, we cannot expect we can do everything. So because not all bundles are simple, right? So we look at the following local model, which already appear pictorially in the previous example of this EABC, but we choose a specific number here. Okay. And it's not very obvious, but first of all, the Kawanyama state always exists and is unique. Okay, so you just have one set up to equivalence. That means I have a bundle, and the bundle defined on P2. You know, there is a fan of P2, so I have a bundle defined on P2. And the important observation is this bundle itself is already simple. Okay, when n not equals to n. When m equals to n, it's not. So when m not equals to n, it is simple. And moreover, you have some symmetry that if you flip mn, then the underlying holomorphic vector bundle are just the same. But keep in mind, equivariant structure change. As a toric vector bundle, they are not the same. But as ordinary holomorphic bundle, they are the same. But we don't care about equivariant structure at this moment. So we just need to assume, m is bigger than, strictly bigger than n. It shouldn't be equal. Strictly. And to achieve simplicity globally, we look at the following embedded graph. So we have a polyhedral decomposition, right? So we have polyhedral decomposition. I don't know how does it look like. Maybe it's very complicated. And then it's right here. So, and I don't know where's the branch point. So we just take away all the possible branch point. Okay. The reason we take away branch point is because we know that those bundle over branch point is already simple. So we don't have any non-trivial endomorphism there. So we take them away. The only thing we need to handle are those that has non-trivial endomorphism. That means those non-branch point. So we run over all the vertex and edges that intersect the branch locus, but that doesn't intersect the branch locus. Okay, so we take all of them. I don't know. If, for example, if this point is a branch point, then I don't consider all this, and we just consider like this one, and yeah, all those vertex and edges do not intersect it. So I look at the following graph. So it's an embedded graph. You just select some edges and vertex, and the simplicity and our simplicity theorem is the following. So this corresponding sheaf is simple, and again, simplicity implies movability. So it's simple if and only if the following three situations happen. Well, one of the following three situations happen. in the case of m equals to n plus 1, this guy has no minimal cycle. That means you don't have, well, it's not the boundary of any two cell. Okay, so a two cell, you have a boundary. That boundary is called minimal cycle. And if this graph has no minimal cycle, then it's simple. In the case of n plus 2, it's easier. It's just a collection of vertex. Okay, just circle dots. And finally, if bigger than that, you simply have no graph. So you cannot have such a graph. As a whole, we can already see that the smoothability can be captured combinatorially in this situation. So it's a pretty elegant result that the hard smoothability problem can be solved by just look at how this graph looks like in B. And so let me just, this is just some ongoing work. Maybe I should skip to the time limitation. We want to study it in a more conceptual way to make it more like, one thing is we want to understand higher dimension and high rank. And example-wise, it's easy, but to get a good deformation theory, so far it's still in progress. And it seems that our shift also related to this log structure in algebraic geometry. But yeah, anyway, so is there any problem? Because I'm going to change to the symplectic world. Is there any question on the algebraic side? Then let me continue to the symplectic world. So as I promised, I will show you how this Kaneyama data, or how to build toric vector bundle by using symplectic geometry and homological symmetry of toric variety. So now we just need to focus on one toric variety to determine when a toric bundle exists there. So first of all, we have the equivariant version of homological symmetry proved by Fang Liu, Schumann, and Saslow, saying that the equivariant perfect complex of a toric variety is quasi-equivalent to the Fukaya category of cotangent bundle of a vector space with asymptotic condition. What is that? So perfect complex, I don't explain it. The Fukaya category here we look at is the asymptotic condition specified by the NR infinity of the following set. Okay, let me just draw you an example what this set look like. So now I have a fan, and to be simple, let's just draw one dimension because I cannot draw higher dimension anyway. So let's say you have a fan of P1, is fan of P1. So you have three cones. One of them is sigma, minus sigma, and 0. Okay. So what is this subset? This subset is inside this MR cross NR, and let me specify this guy. The fan side is the NR direction. Okay. And the MR is the dual of NR. So let me also draw this NR, this MR. So it's a cotangent bundle of NR or cotangent bundle of MR, it doesn't matter, this is self-dual. So what is this? So for each cone inside, now I have 3. I need to take the perp of the cone. Okay, so I look at all the lattice that is perp to it, and times m. So for instance, what is the perp of 0? Everything is perp to 0, right? So everything is perp to 0. So the 0 cone here, we have the whole line. And there's no effect when you add the m. 0 perp is mr. So adding m is still mr. So the underlying set is this line. Okay. So for the other two cones, now this the minus sign get annoyed. It's just a convention by them. And the perp of a maximal cone is 0. Okay, because it's maximal. You need to perp to a maximal cell. You perp to this, then it's 0. And then you need to add all the lattice. Okay. Okay, let me just write down the So I need to have a sigma perp. Okay. And then you need to times the corresponding cell. So if you have a sigma, then you look at minus sigma, and then you times all the lattice. Okay. So you have this line, this line, this line. All these points are lattice points. Okay. And you have the other side, right? You have the other side. So you have this side. So this is the underlying, this is the set. Okay. And what is the asymptotic condition specified by NR infinity? Is that at the infinity of NR, for example, in this picture, you have all these points at infinity. Okay. They are the points at infinity. Of course, you have the other side. And then the Lagrangian that I consider at infinity, you need to sit inside this subset. That means, for example, in this picture, your Lagrangian look like this. Okay, you need to hit at the infinity, these points. And well, if you are mirror symmetry people, you immediately see this. You should be very familiar with this picture. That this Lagrangian will be correspond to O. I don't know how many layers. 1, 2, 3, 4. For example, this one is O4. Okay, it's mirrored to O4. So, well, this is a one-dimensional picture. That higher dimension, I'm sorry, I cannot draw it for you. But we have this condition to emphasize we are looking at this toric okay, the mirror of this toric. Otherwise, if you just delete this, then you have nothing, no information from the fan. So this is this determines the mirror of toric. And moreover, they show that it's compatible with SYC in a sense that it intertwines Lagrangian sections and toric line bundles, as I explained in the beginning. And again, SYC predicted if you add a multi-section, if you add multi there, then this one should be correspond to vector bundle. So what is a multi-section in this case? Again, it's just recall it's a Lagrangian immersion with the standard symplectic structure here, Lagrangian immersion. But this guy is a product of these two guys. They are due to each other. And then you project to NR. Okay, keep in mind I project to NR. So multi-section or whatever section is with respect to this projection. Okay, this is the SYC base. So I just require that this composition is a branch covering map of finite degree. That's called a multi-section. And of course I need to have this admissibility condition. But note that here, having a non-empty branch locus is very important because this guy is simply connected. And if you don't allow a non-empty branch locus, if it is simply connected, all covering map are just several layers, right? If it's disjoint union of all n out, then the mirror will be just direct sum of line bundles. But you have a lot of vector bundle on the toric, they are not direct sum of line bundles. So the non-empty branch locus here of this map capture whether whether you can have indecomposable vector bundle. And one thing I need to emphasize is because Lagrangian multisection may not be exact because you can have topology, we need to switch to Novikov coefficients, okay, to avoid convergence. And let me denote by the following Foucault category, which is just generated by all the tautologically unobstructed Lagrangian immersion. What does it mean? It means that they don't bound any generic homomorphic. So all the moduli, basically saying that all the moduli space has negative expected dimension. Okay, and turns out the mirror symmetry statement is still true over the Novikov field, but we are not proving this directly using SYC. We need to go through what Nadler and Saslow did. by using the factor through the sheaf theoretic side. First of all, go from here to the coherent correspondence to go through go to some sheaf category, and then from that sheaf category to do a microlocalization, and then you go to the Foucault category. So this is a very technical statement, but it's already known, so we can mimic them. And of course, one should ask, because we are looking at multisection, and we are also looking at tautologically unobstructed Lagrangian, then we should ask when a multisection is homological and unobstructed. And together with Jungen O, we show that whenever the dimension is less than or equal to 3, embedded multisections are always tautologically unobstructed. Okay, so this is one of the important results of us that, well, we just don't need to care much about the tautological unobstructed assumption. So any multisection, once it's embedded, is always tautologically unobstructed. So they don't bound any rigid holomorphic disk. And in n equals to 2 there's something more to say. Is when you look at the immersed sector, how they immerse. So you can talk about the immersed point, the degree of the immersed point. If the intersection is always of degree 1, then it's always tautologically unobstructed. Okay. It's a modular counting problem, which, sorry, I won't present the proof here, but you can ask after the talk if you want. And for multisection, there's a canonical grading you can put so that all the fibers generically intersect with L. The degree is always the dimension of L. So to this, we can talk about what we mean by canonical grading. And then we use some microlocal theory to show that the mirror of a canonically graded, of course, you have the admissibility condition. Then all Lagrangian multisection, they are the mirror after you apply mirror symmetry, they are bundled. Okay, they are not perfect complex. They are a perfect complex concentrated at 1 degree. Okay, so that's well. So why is it good to have this? Because once we can construct a multisection with the asymptotics, I will explain later, specified by a tropical object, then we automatically get a mirror. And we tropicalize the mirror again. The tropicalization is this guy. And that means we solve the existing problem. Okay, that's we call, some people call it B-realization, because you are asking whether some tropical object can be realized by some algebraic object. Okay, so and of course, on the other hand, we should call this the A-realization. You will see later. So what is this asymptotics? Then we want to specify is the following. So recall the data of a tropical Lagrangian multisection is a cone complex. You have a collection of cones, a projection map that looks like a covering map, a multiplicity on each cone, and more importantly, the most important part, the potential function, or a piecewise linear function. Then we can define the following subset, which is a subset of this guy. Okay, of this guy. By just looking at all the slopes. Okay, you run over all the slope in the cones of your piecewise linear function. Okay, then by regarding the slope as a coset, this is a subset here. So you can talk about the infinity of this guy. Of course, you can talk about the infinity of this guy. So for example, in that case, infinity of this guy is just specifying which point you are having. This is the sum L trop. And where's the orange? Fine. And this guy is this guy. I should write this one. And this point. So the question is the following: if I give you a multisection L-trop over a complete fan, whether you can find a tautologically unobstructed Lagrangian multisection so that the infinity, the asymptotics, sit exactly inside the infinity of this guy. Okay, that's the A realization. If this is okay, then we apply mirror symmetry, get a bundle, and tropicalize that bundle again is exactly this guy. Okay, so you complete the following triangle. You start with L-trop. You try to construct really an L whose infinity is that one, and then you apply mirror symmetry to get a bundle, and you re-tropicalize it. Okay, so this is the A realization. Okay, so this is the question that we are going to address. So any problem about, any question about this question? Let me just no. So the immediate answer is no. The reason is we know that not all tropical multisection can actually come from vector bundle. So if I give you an arbitrary combinatorial object like this, you may not be realized by this guy. Okay, this is much easier to show. Okay, I can write down your example. For instance, just the fan of P2, and then look at C1, C1, C2, C2, C1 plus C2, C2 plus C1. Okay, and you project to the fan of P2. So this is fan of P2, and it's not very hard to show that this combinatorial object cannot be realized by this guy. So if you cannot be realized by this guy, of course you cannot be realized by this guy. The error going this way. So we must have some extra assumption on it. And again, let's just start with our favorite case, the 2-2 case, dimension 2 and rank 2 or twofold cover. And in this case, because it's a cone complex, so it's a collection of cones, the underlying topological space, L, either is homomorphic to R2, and this projection, the covering map is this square map. If you identify this R2 and NR, NR is also R2, so you identify them with C, then this map is just this set map to set square, like in that case. And the second case is a trivial cover. And I give it a name O and E, and you will feel like odd and even. And I will explain why I call it odd and even. So before that, let me just do some setup. If I choose a circle, so now on the base you have a fan, and then here you have something like this. If I choose a circle around the origin, then you look at the pre-image, it's also one circle. You just shrink the circle a little bit to get this circle. In this case, we have a unique deck transform, which is evolution. And if you parameterize the upper circle, so the circle C, the circle S1, you parameterize by 0 to 2 pi, then the deck transform is nothing but just translation by half. Okay, translation by pi. That's the deck transform. And in the second case, so there's a case O. Case E is a trivial cover, right? Trivial cover, that means you have fan. You just repeat itself. And then you choose a circle. Of course, you have two circles. It's like boring, right? But anyway, let's just parameterize by 0 to 2 pi. And there's a complicated, but not that complicated definition, which says the following. But just look at definition, it's like complicated. Let's just look at photo. so now this is the piecewise linear function upstairs, restrict to C. Okay, so I parameterize by the what's this called, polar coordinate. So I fix R, and then I move theta. So I restrict to this circle. So you get a piecewise linear function, like I just draw it randomly. And then what I did is to apply this function by the deck transform. So if this function apply the deck transform, we will shift to here. And then what I did is I shift the later part back to the first part. So you have this picture. Okay, the later part here is shift to here. So you compare these two by shifting the other side to the other side. Then you may or may not have some intersection points, right? And well, there's a bad name. So if you come up with any good name, please let me know. It's called free generic. Generic refer to the intersection point does not happen at the corners. Free refers to, for example, this case, you have three intersection points. Okay. So and basically, all this word means that picture. You just compare the graph, the two graphs after the deck transform, and count how many intersection points are there. It's easy, it's very doable. And in the odd case, so in the odd case, n is odd. Even case, even. And well, it's just some topological reason or in intermediate value theorem. That's why I call it odd and even. And in the odd case, I can show that using some SYC idea that I won't explain here. But if this guy is n generic with n equals to 3, if it can be realized by toric vector bundle, okay, if it can be realized, then n must be bigger than or equal to 3. Okay, that is like obstruction for realizing the bundle. So you may expect, well, at least it must be a necessary condition. So you may ask whether it is sufficient. So you want to have this assumption, n bigger than or equal to 3. And of course, for the even case, it must realize by two Lagrangian sections because you have two copies. But you will see that it's just a special case in our following construction. So let me just first remove the disk center at the origin. Then, well, it's just this picture, repeat again. So it's exactly C minus a disk or two copies of them. And the branch covering map is after you identify with C, you have the set matrix Z square and the trivial one. And now we can form a Lagrangian as follows. So you have this function, you restrict to the outer annulus, and then you're piecewise linear, right? It's piecewise linear, so you just round the corner a little bit. You're rounding the corner of the function, of this piecewise linear function, and you can differentiate it. So after you differentiate, it's a one form upstairs. But then you need this part, so you push it forward. It's okay because you are away from singularity. So this inverse makes sense. You can push it forward to here, and then take the projection. So this is a Lagrangian, obviously a multisection, but you have something missing. And the n genericity implies embedded. And if you shrink it, shrink the corner, that, I mean, when you do the smoothing, you have a surgery parameter. You just shrink that parameter. When it approaches to infinity, you can achieve a symptotic condition. But the problem is we have something to group back. We need to group back here. And there are lots of choice, right? Lagrangian is so non-rigid, so you can arbitrarily glue a lot of things. But the problem is if you do a random gluing, you may get some immersed point. And your flow field can be obstructed. So to guarantee unobstructedness, we need to choose the local model carefully. And here's why we need n bigger than or equal to 3. Once it's bigger than or equal to 3, you can write like this. And then you take g to be this one, k minus 1, which is bigger than 0. And you look at the following curve. It's a complex curve with the complex coordinate here, and then you look at the polynomial of degree 2g plus 1. And if you're familiar with this, this is a hyperelliptic curve that has one puncture, and the genus is exactly g. And similar for the even case. Okay, you just change the degree to be even. And after doing hyperkähler rotation, they are Lagrangian. And it turns out we can also write it like the standard form that I introduced. The key observation is this function, this phi standard, it satisfies the same n generic condition with the n determined by this guy. So you can try to glue this function together, and finally you will obtain a function defined on the outer annulus, so that you have the desired asymptotic condition, because you don't change the infinity, you just change something around the annulus. And if you choose the leading coefficient of fd large enough, then all the roots are given by all the inverse points are just roots of fd, and all of them are index 1. So by the theorem of myself and Jungen, we know that they are always topologically unobstructed. So as a corollary, we know that the A realization problem is solvable if and only if n is bigger than or equal to 3. And well, when d is even, then it's just this, right? You have a distinguished degeneration of your hyperelliptic curve, and both of them like all are square, so you can take the square root. And in this case, you have two copies, and they intersect, so they just correspond to two line bundles, direct sum together, or two Lagrangian sections, and union them. So applying mirror symmetry, you have the following. At least I don't know this algebraic result. We say that if I give you something tropical, and then you once you do that trick, I mean you compare the number of intersection points. If its number of intersection points is bigger than or equal to 3, then you get an indecomposable rank 2 bundle toric with the following numbers. So higher rank case is actually no more difficult. For any rank, we have the similar theorem, but only the n genericity replaced by you compare with all the other deck transform, not just one. You have a lot of deck transform and compare them. And you look at this local model, turns out the statement is almost the same, only the n has a specific form, which is this 2d over r plus 1, and take the smallest integer of this number. And also you need the GCD to be 1. And in this case, you can always get a bundle. And there's some example that I didn't draw you, but for r equals to 3 and d equals to 2, there's an example also on the fan of P2, which has genus 1. And okay, let me just stop here and lift it to the question.
Any question for the speaker?
So in this toric setting, is it possible to encounter orthotropic manifold?
Well, that's a very good question. For coisotropic brains, I think the main reason is we don't really know how to tropicalize coisotropic brains. And secondly, I think in the toric case, we are close to the large volume limit. So we don't need coisotropic objects.
Okay, so you don't think that will occur?
Yeah, but in the Calabi-Yau case,
already somehow complete without.
Yes, you don't need the idempotent object.
And then also on the Lagrangian submanifold, you don't add a flat line bundle. Is it because it's always trivial?
And no, you can actually put a flat line bundle. For multisection, because you may have topology, like I explained, you can have like genus 1,
Right.
you can put a flat line bundle on it. And you just have a bigger modular. The modular space is there. It is controlled by the H1. It's there actually. So you just change the gluing the modular parameter.
But you still have a homomorphic vector bundle.
Yes.
on the other side.
Yes. Yes.
So any other question or comments for the speaker? Okay, if not, just send our speaker again.
Thank you.